Georgina. I'm going to be presenting work by myself and my colleague Richard Siddans, Brian Kerridge and Barry Latter back at STFT RAL in the UK. I'm going to talk about the principle of combining UV and visible spectra predominantly in order to get to the surface, really, or near surface information about ozone. So I'm going to start off with talking about what we do, essentially UV profiles. I'll talk about the challenge of retrieving ozone using visible information, the idea about combining this information, the visible and the UV, in an optimal way, and then show some results of simulations. Then I'll go to some results from some real measurements over 2 wavelength ranges using 2 different approaches, and then talk about the future. So at RAL we have an ozone profile retrieval algorithm that's really optimized for tropospheric ozone. We're part of the ESA Climate Change Initiative, which is producing climate quality variables from satellites. And as a result of that, next year we'll be processing the entire emissions from GOME, SCIAMACHY, GOME-2A and B, and then OMI, which will be data that's publicly available. We're currently working on combining visible information and infrared information from IASI, incorporating that into our UV retrieval to make use of their complementary vertical sensitivities. Just at the bottom there, we've got an example of some output from our UV-only profile retrieval of the lower troposphere. This is for June in 2008. So you have our product on this side, and on the other side you have the equivalent result from a chemistry transport model. So you can see that the satellite product really does pick out the interesting features that you expect to see, the low in the Pacific here, and the enhancement in the Northern Hemisphere, and particularly over the Mediterranean in the summer. So why do we want to improve the sensitivity to near-surface ozone? Well, it's often talked about how boundary layer ozone and near-surface ozone impacts crop yields and damages ecosystems, which have financial implications. It also impacts air quality, both excess deaths, there's been a lot of work on that, morbidity and mortality outcomes. We are quite limited to in situ observations, which are point measurements, and otherwise we're quite reliant on air quality models, which are quite less well understood in their terms of their performance above the surface. Passive nadir techniques, both in the UV and the infrared, are very limited physically into how far down in the atmosphere they can penetrate, both from scattering and thermal contrast. So really, visible channels offer the only opportunity to penetrate down to the near surface. There's some future missions, the Sentinels from Europe, Tempo and GEMS, which we're going to have improved spatial and temporal coverage than GOME-2, which is what I'm going to talk about today. But not all of these instruments will cover the Chappuis bands, which is where this visible information is. But it's a very difficult problem to do. So in the visible, typically you have less Rayleigh scattering, and the land is brighter than over the UV, so you should have better signal to noise. However, it's very the Chappuis ozone band is a broadband feature, so there's a limited amount of information that you can get from that, and also there are a lot of other spectral patterns that interfere with your fit of ozone. So over here we have some other trace gases that interfere with your Chappuis ozone. So the Chappuis ozone is this black line, and over to the Wolf bands and the O2A band there. But the principal worry really is the spectral shape of the surface, which varies from pixel to pixel, with time and with space and season. And here we just have a selection from an ASTA USGS database of different land surface types and spectral shapes, which always all interfere with your attempt to try and fit this ozone feature. So as I mentioned, you really only have one piece of useful information in the Chappuis bands. You can't retrieve profiles from the Chappuis on their own. And you can do some simulations, radiative transfer simulations and retrieval simulations that show that actually you can start to get some information about boundary layer ozone if you're able to fit the slant column in the visible to within a precision of about 1%, which is a massive challenge even in the UV. And there's some more information about that in a report from a few years ago. But what we propose to do is to combine the information from the UV profile with the Chappuis slant column in an optimal way using a linear retrieval step. So essentially you use your Chappuis slant column as your measurement, your UV profile as your a priori, and you make a weighting function essentially which describes the differential light path sensitivity between the 2 wavelengths. So this is a very good illustration of how essentially the light path penetration into the troposphere is improved in the visible frequency as compared to the UV. So this is really the physical limiting factor of why you can't see down to the surface at other parts of the spectrum. So I'm going to talk about two approaches that are really derived for 2 different reasons. and also using two different wavelength ranges. So first of all, looking at a physically based DOAS slant column fit, which is much as a conventional approach. The second approach is more of a mathematical approach, where we just use radiance measurements from GOME-2 and a UV slant column and no other physical information. And you can use the UV slant column to train your patterns from an SVD-based approach in order to explain the variability of ozone just using the measurements. And the other patterns essentially that from that take care of everything else. We're looking at two different wavelength ranges, 450 to 550 nanometers. This is because this avoids the band overlap for GOME-2, which can be tricky to fit across. And secondly, it's also the region in the Chappuis bands where you have most differential structure, so potentially that should be easier to fit. The second wavelength range, 550 to 670 nanometers, really takes into account the whole of the Chappuis bands. Yes, so I'm going to talk about that afterwards. So first of all, how well can we fit a slant column using just visible information? Well, it turns out quite well with a bit of care. So over here you have a monthly mean total column derived by just using a geometric AMF to the slant column, just derived using UV information. And over here is a Chappuis equivalent. And as you can see, they look very similar. And looking at a raw correlation, the slant columns are very similar to the point where it's actually the differences that start to become interesting. So this is for August using cloud-cleared radiances. But before you go any further, we want to understand what signal we can expect to see using in the Chappuis slant columns. What signals will be retained? So over on this side, you have modelled ozone in the boundary layer. So this is the chemistry. This is Tomcat, a chemistry transport model. This is a 0 to 2 kilometre subcolumn above the surface as a fraction of the total column. So you're looking at anything from 1 to maybe 5 or 6%. So it is quite a small signal. What you can do is you can simulate the slant columns in the UV and the visible, and then look at their differences. So here we have, using Tomcat profiles, so this is model profiles using the instrument viewing geometry and the surface albedo. You simulate these two slant columns and then you look at the difference. And what you can see is that the differences between the slant columns do start to describe really the differences in the boundary layer. So all of this difference is coming from the differential sensitivity that you get from the visible. You can do the same in the stratosphere and look at where the differences are coming from in the stratosphere, and really they're very, very similar slant columns in the stratosphere, just high latitudes that you get a difference. And you can use this stratospheric simulation essentially to correct the difference in the troposphere. So then you know that all the differences you're looking at here are coming from the troposphere. And now you're really starting to see the shape of the boundary layer ozone that's reflected here, especially over Africa and Europe and even over North America. So we know there is a signal that can be retained in this Chappuis slant column that is not there in the UV. So this is some results from real measurements using a DOAS conventional slant column fit in the month of August. So these relative differences that we saw in the model before, this is actually using real measurements. So this is a UV slant column derived in a conventional way versus the Chappuis slant column. And then you have the model field there as well of the expected boundary layer ozone. So you can see that in some places, you're seeing ozone enhancements where you hope to see it. But it's also very clear here that you're seeing some features associated with land surface types. This is where the spectral shape of the land surface is interfering with your fit of ozone, especially over places like Sahara Desert and certainly the Himalayas and then maybe even the Rockies. And you can tell it's from real measurements because you have the South Atlantic anomaly quite evident there, where it gets very noisy. But one good thing to come out of this was the fit of NO2. This is not a conventional fit window for NO2, but the slant column for NO2 actually looks quite nice. And when you can use a reference sector, your tropospheric NO2 actually also looks pretty good, which is a very encouraging aspect, showing that the fitting in principle is working quite well. So now onto this SVD-based approach, using essentially more mathematical approach with no other physical information except for the UV profile to train your patterns from the measurements. We have this relative difference and then the stratospheric corrected relative difference using simulations. And here you can actually see things working a lot better. First of all, it's a much less noisy field. So you're looking at differences within the precision range that we really need to be looking at from simulations that show you need to be adding information. So if you look at this relative difference compared to the boundary layer distribution of ozone, you're seeing enhancements would really like to be seeing in the enhancements. So although it is still quite noisy, you can see enhancements over China, over the Arabian Peninsula, and starting towards Western Europe. So, and the only difference between these is the vertical sensitivity from the visible versus the UV. So just to recap, we've used multiple approaches to really get at this very difficult problem, to try and get complementary insight into this. It does look like, actually, for the most cases, we can fit the slant columns in the Chappuis to a sufficient precision where we're going to be retaining information about near-surface ozone, which we can then combine with the UV profiles in an optimal way. The DOAS approach currently doesn't work in the tempo spectral range. This is partly because of the GOME-2 band overlap, which is very difficult to fit across using DOAS. But it also could partly be with the issue between land versus ozone. If you overfit the land, you start taking information away from ozone. So it could be to do with the way that we haven't quite pinned down the fit of the surface spectral shape yet. The SVD approach gives good results in both fitting windows, but it's a little less intuitive really to understand the things it's responding to. In terms of next steps, we still expect to be able to make some improvement on characterizing the land spectral shape, some of the scattering processes, and spectroscopy, which can be an issue as well in the Chappuis bands. Tempo potentially should have a better handle of surface spectral shape. There are observation techniques where you can make assumptions about how the colour of the land essentially doesn't change between measurements, even though the absolute radiances do, which GOME at the moment isn't able to do. So our next major step is to apply this linear combination to more results, to the whole of the GOME-2 mission, and then evaluate how this changed sensitivity to ozone in the boundary layer performs, whether it changes things in a good way. And we expect to be able to work towards a publication next year on this work and take it another step. And just to finish, this is our unconventionally fit NO2 over North America for 2008, which actually I think looks quite good. I'll leave it there. Thank you.
We have time actually for a couple of questions. Are there any questions?
I got a question. I wonder if you care to speculate. You know, there's been this neural net technique, which has been giving spotty results, which you might expect because, you know, you're using their land surface types different. Do you see a similarity in your SVD results and the neural net results?
Well, I haven't compared them directly, but I do know that if you just take the measurements, the GOME-2 measurements, the sun normalized radiances, you can actually see up to 30 surface patterns, 30 leading surface patterns that are required in order to fully characterize the surface, which is a lot. Obviously, the more patterns you fit, you're taking away information from ozone potentially, but if you don't fit them, you'll end up with an ozone product that is very correlated to your land type. So I mean, the techniques that we've been employing are essentially linear regression, whereas neural nets are non-linear regression, essentially. So I mean, potentially you could see similar results, but I haven't compared them.